In this chapter, in this topic, if you will, we follow frequency distributions, histograms, various graphs, scatterplots, correlation, and regression, although we cover that with more details later on. So the objective would be to organizing data using frequency distribution, representing it accordingly with tables and graphs, bar graphs, time series graphs, pie charts, and various types of plots like stem and leaf plot. What we covered in previous topics, we discussed the meaning and definition of statistics, which is the science of planning, studies, and experiments, obtaining data. Then we looked at data, which is collection of observations. Population, which simply means all subjects of interest. Sample, it is simply a portion of a population. Census, when the data comes from every member of a population. Voluntary response sample, one which the respondent decide to answer or not. Statistical significance versus practical significance. Statistical significance is achieved if the probability of an event is at 5% or less. And practical significance, in short, refers to whether it's worth it or not as far as the human being is concerned, which is normally subjective. We looked at types of data, and remember, data are either basically qualitative or quantitative. And in the case of the quantitative, it's either discrete, that means countable, that means whole numbers, 0, 1, 2, 3, and it continues indefinitely, or it's continuous, which means it can take place over an interval. There were various levels of measurement that we discussed: nominal, ordinal, interval, and ratio. Also, a very important definition, a parameter, which is a numerical measurement describing a characteristic of a population, versus a statistic, which describes the characteristics of a sample. And then we looked at an experimental design versus an observational study. It's important to distinguish between the two. In the case of an observational study, we simply observe and we make note of what's going on, whereas in an experimental design, you have to apply some sort of a treatment, and that would be distinguishing between the two types of studies. We discussed different types of sampling. The main ones that we are concerned with are random sampling, systematic sampling, stratified sampling, cluster sampling, and in many cases, one may have to use convenient sampling. Sometimes there is no choice. When we do different studies, it could be that data is observed at one point in time. It's called cross-sectional study. It may go back in time, retrospective study, and it may just simply continue, okay, as a cohort prospect. So this is what we have covered, and now we're going to move on to new stuff. We are looking at this section discussing frequency distribution for organizing and summarizing data. So the key concept is, when working with large data sets, a frequency distribution or frequency table is often helpful in organizing and summarizing data. A frequency distribution helps us to understand the nature of the distribution of the data set. First, we start with what's called a raw data. In short, whatever we collect, just the way it's given, it's a raw data. Now, frequency distribution or frequency table, that's what we want to see what it is as far as definition. Could somebody read this definition for us, please?
A frequency distribution is the organization of raw data in table form using classes and frequencies. It shows how data are partitioned among several categories or classes by listing the categories along with the number, frequency, of the data values in each of them.
Perfect, thank you. And nominal or ordinal level of data that can be placed in categories is organized in categorical frequency distribution. The same type in essence. Let's look at a very simple example. We want to construct a frequency distribution for this case. When the raw data is collected, we just make a note of the data. This is referring to some sort of a plot type. For example, when we see A, B, B, that means the first person, the plot type for the first person is A, then the next person is B, then the next person is B again, and it moves on. So as you can see, it's a raw data, and it may not be that useful. So let's see what happens next. So we want to put it into some sort of a table. In any order that you want to set up your class is fine. This is one order, A, B, O, and then AB. I hope everybody understands what we mean by tallying. Tallying simply means for A, you can, as soon as, just for the sake of argument, you see the first one, you can tally for A and cross it out, and the next A, and so on and so forth. The idea of the tallying is to help us write the next column. So the tallying itself is really not that big of a deal. You want to be extremely careful, however. So again, let me just go back to that A, and then we have another A, we have another A here, we have another A here. So that would be the tallying. In a sense, you can cross it and write it. And so now you put the numbers. So in front of A, when you count, this count as 1, 2, 3, 4, 5. You do the same thing for the rest of them, and you write the next column. So I hope you realize this is it, and you're done. Believe it or not, this is the frequency distribution table. The tallying really doesn't count. Okay, it's just there to help us come up with the answer. So the column that matters is the first column I'm going to refer to, and the second is not important, and the third column. The first column and the third column together give us a frequency distribution table, and you're done. End of the story. However, for more information, we can move on and do other things, such as percent frequency. Percent frequency, by definition, is the frequency divided by n. So what is n? N is the total sum in this column. That is the total size. If you add them up, that becomes 25. I hope everybody can see that. We can add them up. And then from here, for example, this one would be 5 divided by 25. This one would be 7 divided by 25. 9 divided by 25. And the last one is 4 divided by 25. And what you're looking at, this is known as relative frequency. Of course, 5 over 25, as an example, simplifies to 1 over 5. Everybody knows that, and you should do that. And then any relative frequency can be changed to a percent frequency. In essence, both of them are the same, but there's a slight difference between the two. They end up being the same number. I want you to know that. So the relative frequency is F over N, if you will, the formula that you see here. You can change it to a percentage and call it percent frequency. The other thing that I want everybody to understand is this very last formula. When you add up this column, the relative frequencies or percent frequencies must all add up to 1 or 100%. And if they don't, it is because of the rounding error, or we've rounded it. So this is the synopsis of frequency distribution table. We are going to move on to the next example. The next thing is, if we are given data and we want to come up with a frequency distribution table, if it's categorical, we looked at it, but if it's numerical. So first, we have to decide what is our lower class limits, and all of them will be explained with a very simple example. The smallest numbers that can belong to each of the different classes, and upper class limit would be the same row, if you will, but the largest one, the largest numbers that can belong to each of the different classes. Class boundaries, the numbers used to separate the classes, but without the gaps created by the class limits. That's important, without the gaps. Again, all of them may be difficult to follow without an example. We will shortly look at one and we make some sense out of it. Class midpoints, the values in the middle of the class, and it's very simple. Just add up the lower limit and upper limit and divide it by 2. Lower limit and upper limit divided by 2. Class width, the difference between two consecutive lower class limits in a frequency distributions. What is the procedure for constructing a frequency distribution? If we are supposed to make one up, what do? First, we select the number of classes. If we select too many, it really defeats the purpose. Normally it's between 5 and 20 as far as the course is concerned and the exam questions and so forth. Normally it's given to you. The class width, you want to approximate that. Max minus mean divided by the number of classes, that would be the width. And you have to round up always because you want to cover all the data. You want to choose a value for the first lower class limit by using either the minimum value or a convenient value below the minimum. You'll see what we mean by that. Using the first lower class limit and class width, list the other lower class limit, list the lower class limits in a vertical column, and then determine and enter the upper class limit. Take each individual data value and put a tally mark in an appropriate class so you can figure out it belongs to which class. So what do we mean by that? Let's look at this simple example, see if we can make some sense out of it. So we want to construct a frequency distribution table, FDT, and the record high temperature for each of the 50 states using 7 classes. So we are told how many classes. So I have marked the smallest number and the largest. I have put them in a different color, okay, class? So we see the smallest number, we see the largest number, and now what we do, we calculate the width roughly. Basically, we decided what we do is very simple. The largest minus the smallest. That is actually the range, it's called. So we calculate the range and we divide this by 7. So those two steps shouldn't be a big deal. So first and foremost, we find the smallest, we find the largest. Then the difference is called the range. And the range, sometimes we just write R equals max minus mean or high minus low. Okay, the largest value minus the small. So the width is 4.86. And so you want to come up with the width, which is going to cover everything. So 4.86 makes it crazy. We're going to go for a simple number and we're going to round it up. Always round up. So obviously, I hope everybody is clear as to why we choose 5. Now, we want to choose a convenient piece that is as the lowest number. Now, these numbers are very straightforward. So you can even choose 100 as the starting point. That is a good point to begin with. Now, so I hope everybody is clear. Now, you don't even have to use 100. You can use other numbers, okay? But if you use any other number, it has to be less than that. But you don't want it to be too small because at the same time, if you look at the width is a little bit larger than what the actual width was, okay? We chose 5, right? So for the sake of argument, if you start with something like number 90, you may not make it to the last number, to the largest number. So you got to be careful when it comes to that. And if you pick something like that, at the end, you can readjust. So 5 is easily understood. So we are going through the tables. So we know we're going to start with 100. So how do we fill up this table? All right. It's important to remember the meaning of the width. The width is 5. So the next number, okay, so the first one is the row 102. We figure out what number. It is the next one that we're going to put here, 100 plus 5. That would be the lower limit of the next class. Let me make sure everybody understands how we arrive at those. So first and foremost, I want you to understand if the first one is 100, the second one is 105. Now we're going to add 5 this way. Add the width equals 5. So 100. 105, 110, all the way to 130. Why is that? Count 1, 2, 3, 4, 5, 6, 7 classes. Now, I want to look at the upper boundary. The upper boundary, the way it is class, if you use one class, okay, for example, look at the very first one. If you look at this class, the width using the same class is defined as upper limit minus lower limit plus 1 unit. I want you to pay attention to this formula I'm giving you. I'll put that in your formula sheet as well. The width is the upper limit minus the lower limit plus 1. So you have the width, you don't have the upper limit yet. You have the lower limit to be 100 and 1. Let me explain the 1 unit. If 1 represents 1, so be it, but 1 unit may represent 10,000, or 1 unit may represent 0.1. That's why I say 1 unit instead of simply 1. And this is simple math, everybody can handle it, and it becomes 104. And then after you find the very first upper limit, keep on adding 5. Okay, class? 104 plus 5, 109, plus 5, and we get to the end. Now, when we get to the end, make sure you see we have 134, and the last one is also covered. Okay, so this last one is also covered. We are okay with that. Otherwise, we have to rethink what we are doing. So this is it. This is class limits, and we are okay with that. Now, we are going to look at the class boundaries. Now, without the class boundaries, by the way, class, we fill up the third column, which is the frequency, we are done. The frequency distribution table is done when you have this very first column and this last column, which is frequency. Now, how do you do that? It's by tallying. However, let's look at the concept of a class boundaries. The way the class boundaries work is very simple. Remember, there is a gap between 104 and 105. Everybody can see that, right? Now, boundaries say there is no gap. So you add up 104 and 105, you divide by 2. So 104 plus 105 divided by 2. And that's 104.5. And that is the upper boundary of the first and lower boundary of the second class. So take a look at those two numbers only, everybody. 104.5. I hope everybody understands how we arrive at 104.5. What about the rest? Very simple. Add the width. All of them, just add the width. For the first boundary, the lower boundary of the first class, subtract 5. So notice these two are the same, these two are the same. So that's the idea of the boundaries. So how do you come up with the boundaries? You come up with the upper boundary and lower boundary of the upper boundary of the first class, lower boundary of the second class simultaneously, and the rest you just add the width. For the lower boundary of the first class, you subtract the width. Now, what about the frequency? Very simple. You just go and figure out where everything belongs. Now, I didn't put the tallying here, everybody. I want you to know there is no tallying here. But just for the sake of argument, between 100 and 104, just as an example, okay, I want you to know that 100 is in that class. This is one of it, okay? Is there anything else that belongs to that one? Because that's fairly short. I want to make sure everybody gets that. Is there any other number that you can see that it's between 100 and 104? It does include 100, and it does include 104.
104.
So we have a 104 too, right?
Yes.
So therefore, the frequency for the first one is 2. You can figure out the rest as well. Now, what I want to add, is this, the difference between the limits and the boundaries, so everybody understands how it works. The way the class limits work, if you look at the very first one, 100 to 104, 100 is there, so is 104. If you look at the boundaries, 104.5, I'm just discussing the very first one. 104.5 doesn't belong to the first class. If you follow the boundaries mean everything starting from 9.5 all the way to 104.5, not including 104.5. 104.5, if it happened to be there, belongs to the next class. So I hope it's clear so we can move on.
Professor, I just had one question. So,
of course,
you've put 104 plus 105 divided by 2?
Absolutely. In order to find the boundary of the boundary for the first class, the upper boundary, and the lower boundary of the second class. Here's another one. Take a look. If I were to find the boundaries, look at these two. If you add these two up and divide by 2, you get 119.5. So take a look at the upper boundary of this class, which is 1, 2, 3, 4. The upper boundary of class, fourth class, I hope you see this is class 1, 2, 3, 4, 5, 6, and 7. So for the fourth class, the upper boundary is 119.5, and the lower boundary for the fifth class is the same. Does that answer your question?
How did you get first a lower class boundary?
Lower class boundary, that was a choice. Take a look at this one. You have to choose a convenient piece that is either smaller than the minimum value you have, or it's equal to that. So we chose 100.
What is? I'm sorry. I might have I might have said something wrong. What I meant is, how do we choose 99.5 for the class boundaries?
No, we don't choose it. We calculate it.
Okay.
Okay. 100. Okay. So 104.5. Okay. Look at, so everybody's okay with 104.5 as the upper boundary of the first class? Yes? Everybody?
Yes.
Subtract 5. What do you get?
99.5.
Why are we subtracting 5?
Because that's the class width.
That's a class width. Beautiful.
Okay, perfect.
Okay.
Thank you.
I actually have a quick question. So if we do have the value 104.5, it would go in the second class, not in the first class?
It is the upper boundary of the first class, and it is also the lower boundary of the second class.
So when we were calculating like the frequency and we had the value 104.5.
Yeah, if you had, exactly. If let's assume the number 104.5 is also part of the data, then it belongs to the next class. That is by definition of a boundaries.
Okay, so then we would count it in the 8, not in the 2?
Exactly. Yeah, exactly. Here's another one. How about if we have a class, if we have number 124.5 as a piece of data, where would you put it? Number 124.5. Which class?
6.
Sixth class. Is everybody clear? How about 129.5?
7.
That's it.
Okay.
Is everybody okay with that?
Yeah.
All right, let's move on. We want to come up with frequency distribution table. So just to make sure, okay, there's a lot of piece of data here. To do that, this is drive-through service for fast food. So we got to figure out the width. All right. So I hope everybody is clear as to how we arrive at this. The width ends up being a whole number 45. Now, if you want to start with 83 as the minimum value, there is nothing wrong with that, but it's really not a convenient spot to start. And notice the width, which is 45. Again, we want to make it nice and easy. If you decide to go with any other numbers, just to make things up, let's say instead of the width being 50, you want to make it 46. There's nothing wrong with that, but it's not a nice and easy number. I hope you understand the concept. So when you go from 45 to 50, it is your choice. We are choosing to make life easy, okay? And so this is another one. So how do we calculate the width? The range divided by the number of classes. And we already know that we have 5 classes. Take a look. We have 5 classes, okay? And so with that being the case, we can start with number. We can start with 80, okay? We can start with 75. But you really don't want to go lower than that. Maybe even 70 might work, because it's important when you're done. The largest number, 308, must be included. If it's not, then there is something wrong. So it's important to know that a lot of things is really up to you, okay? So the class width is 45, and you change it to 50, okay? When you calculate it. Where do you begin? You begin wherever you like. You can begin somewhere smaller than 83. You can start with number 80. There is absolutely nothing wrong with that. I hope everybody is clear. So with that being the case, let's say we start with 75. Now, can you tell me how we arrived at the rest of them? How did we come up with 125, 175, 225, and 275?
You keep adding 50.
Mm-hmm. Beautiful. Now, how do we get, I'm just interested in the first class, 75 to what? To what number? So my first class is 75 to
124.
one more time, 124. Because remember, the width is upper limit minus lower limit plus 1. And remember, by 1 we mean 1 unit. So it's not 125, it becomes 124. Then all you have to do, add 50 to that column. Keep on adding 50. So I hope you see that it's not difficult to find these numbers. Never mind the frequency, I want to discuss the upper limits. So what are the lower limits? The lower limits are 75, 125, 175, 225, and 275.
I just have one quick question, Professor.
Yes.
We made the width 50 just out of convenience in order to better
exactly.
Organize that time,
It is absolutely up to you, and it must be larger than 45. So in other words, you can't say 40. That would be a wrong choice.
Okay.
You can choose 60, but it's way off. You know what I mean?
Yeah.
It's out of convenience, absolutely. So 50 is very straightforward. The thing is, why did we choose 75? I want to stick with that, but you can choose 80. In fact, I highly recommend, if you have time, try it with number 80 and see how that works. So the lower limits and the upper limits are clear. How do we come up with this one? As you can see, it's just a matter of tallying by now. It does take some time to do the tallying. Okay. Sounds good, everybody? Now, the next thing, so practically we're done here. I want you to know that, but we're going to add some stuff for information. Now, obviously, n adds up being 50, the same number that we had there, the total size. Okay, if you add up, that's another thing that you want to be careful. You always add them up, make sure you come up with the same size. Otherwise, we've made a mistake somewhere. So this is a good way to check your work. Now, as far as finding the relative frequency, as always, okay, remember the relative frequency would be what? Just the frequency divided by the total size. So the relative frequency for the first class would be 11 divided by 50. The second one would be 24 divided by 50, so on and so forth. So how do you calculate the relative frequency? It's very simple. Divide f by n, okay, class? Divide f by n, and you get to the answer. I hope it's straightforward. And how do you change it to percent frequency? Again, you should have no problem doing that basic algebraic technique, okay? You can always change to a percent. And remember, they must add up to 1 or 100%. I can't really emphasize this enough. The only time it doesn't, when you have a round of error, okay? So that's one of the things you want to be careful. Don't round it too early, okay? If you have to round it. All right, let's move on. All right, I'm assuming everybody is comfortable with what we did, so I'm going to repeat the same table, okay? So what you are looking at, class, what you are looking at is from the previous page, frequency distribution table, FDT. FDT, frequency distribution table. Now we are interested in cumulative frequency distribution table. So we want C F dt. Okay. How do we arrive at it? There are 3 ways to do that. So I'm going to look at all ways, and my favorite one is this one. So how do you come up with C F dt? You look at the first column, and the lower limit of 75 remains for each and every one of them. What does it mean? It means cumulative. It means from the get-go. And therefore, 75 to 124 is the same good old 11. So that repeats. But what happens to the next one? Now 11 plus 24. What happens to the next one? 11 plus 24 plus 10, and then you add 3, and then you add 2. Okay? Or you may use this method, as some texts they use, less than 125. They use the lower limit of the next class and they write it less than that. Or they use the boundaries and they say less than the upper boundary of the first class. But all of that mean absolutely the same. I'm more interested in that. However, and this is what I like, if we had on-campus exams, this is what we would use. I mean, either one of them, you get full credit from me. However, as you do your homework or exam questions, just follow the way they want you to do it, and you get full credit. I hope everybody understands the meaning of this table, the cumulative. Sounds good? Okay, so it's very simple, you add them up. The thing that you want to be careful is the following. This one, this number must always be n. If you haven't made a mistake, this must always equal number n, whatever it might be. All right, so that's that. Let's move on. Could somebody read this one for us, please?
Critical thinking using frequency distributions to understand data. In statistics, we are often interested in determining whether the data have a normal distribution. 1. The frequencies start low, then increase to 1 or 2 high frequencies, and then decrease to a low frequency. 2. The distribution is approximately symmetric. Frequencies preceding the maximum frequency should be roughly a mirror image of those that follow the maximum frequency.
Thank you so much. Later on, we will pay more attention to this. This is the core of the course, and it will look something like this. This is called normal distribution. Now, of course, in reality, nothing is 100% normal, but something close. That's the idea behind that. Okay, somebody read the second part for us, please.
With gaps.
Gaps can show that the data are from 2 or more different populations. However, the converse is not true because data from different populations do not necessarily result in gaps.
Thank you so much, everybody. All right, so let's look at this table, okay? Just as an example, this shows the frequency distribution table, okay, FDT, for what? Weights in grams of randomly selected pennies, okay? And so the idea is, and again, we may not know the information, and I don't expect you to know this information, but the idea behind this is that we notice there is a gap. So probably we have 2 different groups, and we may stop at that. However, a piece of information says pennies made before 83 are 95% copper and 5% zinc. After 1983, things are different, 2.5% copper and 97.5% zinc. So that's why it changed its weight on the average, okay? So again, that's a piece of information we may or may not have, and it's not important. The gaps can sometimes reveal things. All right, we're gonna move on. Sometimes when we combine relative frequency is, or frequencies, if you will, then we can get something out of it. So in this case, the table shows the relative frequency distribution for the drive-through launch service time for a fast food. So we are dealing with fast food and coffee shop, okay? And so it shows the time, for example, if we discuss the very first class, the fast food doesn't give us any piece of data, but the coffee shop, 22%. And when you move forward and you look at this, you should be able to see that there is a big difference. And normally, if you go to a coffee shop, the service takes place in a very short time. That makes sense. Whereas fast food is not as fast. That is a normal expectation class. So, all right, we want to identify the information here, such as class width, midpoints, boundaries, and so on and so forth. All right, class width. There are really 2 ways to do that. You can pick any 2 classes, any 2 consecutive classes. Whether you do the upper limits or lower limits makes no difference, class. The difference is the answer. Or if you pick one specific class, upper minus lower plus 1. So I hope everybody is clear as to why the width is 100. By the way, if you count from number 100 to 199, including 100, there are 100 numbers. I want you to know that, not 99. So one more time. If you count from 100 to 199, including the endpoints, namely 100 and 199, that is 100 pieces of numbers. So the next one is asking for the midpoint. The midpoints basically add up, divide by 2. So for the first class is 100 plus 149 divided by 199, I'm sorry, divided by 2. And then you don't have to calculate the next one, add the width. So all you have to do, calculate the first one, class, which is 100 plus 199 divided by 2, giving you 149.5. Then add the width. Add the width, that's all. So you calculate just one of it. That's all there is to it. And what about the boundaries? Remember how we arrive at the boundaries. Let me just use a different color again. So add these 2, 199 and 200, and divide by 2. The midpoint of the 2 is 199.5. And then just keep on adding the width. And for the first one, subtract it. Finally, number of subjects, add the frequencies. Add them up. 25 plus 92 all the way to the end. That should be very straightforward. All right, let's quickly look at the last question before we move on to the next section. All right, could somebody read the question, please?
Analysis of last digits. Weights of respondents were recorded as part of the California Health Interview Survey. The last digits of weights from 50 randomly selected respondents are listed below. Construct a frequency distribution with 10 classes. Based on the distribution, do the weights appear to be reported or actually measured? What do you know about the accuracy of the results?
I'm going to assume everybody can make up the table very nice and easy. When you look at the last digits are 0 all the way to 9. So you can tally, you can make up this table. I'm assuming nobody has any problem setting it up. Okay, but when we look at this, and this refers to what are we measuring here? A lot of weights, right? As you can see, we have too many zeros and 5s. So that means what? Basically, it was approximated. And so it can't be accurate. And by the way, after 0 and 5, number 8, we have a lot, okay? Sometimes, I don't know, instead of saying 170, we say 168. That may be the case. But more importantly, too many zeros and then too many 5s, and that has the indication that we didn't actually measure.
May I ask a question?
All right, go ahead.
How do we calculate the probability that that these frequencies are actually true, that this isn't inaccurate data? Because there is some chance that, for whatever reason, there are, but a low chance, granted.
No, understand. Understand what's happening. This is based on the data. You remember, a lot of stuff in statistics could be interpreted subjectively. We are saying if this, we don't know that for sure. It could be, yes, by chance. Yes, you're right. It could be that, a lot of people, they measure and end up having weights that end up with 0. But if you are looking at a normal distribution, it can't happen that 0 is more than the rest of it. So based on your simple observation, you say, well, this makes no sense to me.
Okay, so it's a subjective kind of.
Yes, but more importantly, it could be subjective, but at the same time, it's a decent guess. How come we have so many zeros? If it's a normal distribution, the normally distributed, and the weight is normally distributed, then zeros and 1s and 2s and 3s and 4s, and they must be close. They can't be that we have too many zeros. Okay.
Okay.
I hope this answers the question.
Oh, yeah, absolutely.
We looked at the previous section, FDT, frequency distribution table, and what they mean. Frequency distribution table refers to organization of raw data into a table. We have the lower limit, upper limits, class boundaries, class midpoints, and class width. Each one is calculated accordingly. And the procedure was discussed as to how to come up with the frequency distribution table. All right. What we are going to do in this section, going to look at the histogram, and while a frequency distribution is a useful tool for summarizing data and investigating the distribution of data, another tool would be histogram, which is a graph that is easier to understand and follow. A graph consisting of bars of equal width drawn adjacent to one another. That is the synopsis of what's a histogram. The horizontal scale represents classes, quantitative data, and that's important to follow. And the vertical scale represents either frequencies or percent frequencies. Important use of histogram visually displays the shape of a distribution, shows the location of a center, and the spread and outliers. So here's a simple example. Again, we have seen this now. We want to look at its histogram. So I hope you see the concept is very simple. You go with a simple grid, and along the x-axis, the horizontal axis, you can put these numbers. The way the horizontal axis works, you have 3 choices. You can choose to use the limits. You can use the boundaries. You can even use the midpoints. However, later on, we discuss a graph called ogive, and in that case, we have only one choice, and that is using the boundaries. And because of that, it's a good practice that we use the boundaries along the horizontal axis. So I would use the boundaries here. So you would put, for example, 99.5 here, and then 104.5, and you move on, you make up your scale. Now, on the vertical axis, you have a choice of using frequencies or percent frequencies or relative frequencies. Which one do you use? Whatever that you are asked to use. In this case, we use the frequencies. For example, if you look at the very first one, and the height, you can go, in this case, 2, 1, and so forth. So you can go from the scale, if this is 1, for example, go all the way to, I don't know, what is the largest one? 18. You can even scale it such that the largest one, I don't know, is 20. And you just pay attention to your scale. I hope everybody can come up with this simple histogram. The bars are adjacent. Look at the bottom as your horizontal axis. It contains the boundaries. And again, I'm going to repeat, you can use the boundaries, you can use the limits, you can even use the midpoints. But the best choice, boundaries. Why? Because there's a restriction for some graphs that they must use the boundaries. Therefore, it's a good choice to stick with that. Now, your vertical axis, notice, in this case, is frequency, because frequency is given. If they want us to do percent frequency, ultimately, it really looks the same. I want you to know that it doesn't make that much of a difference. Whether we use frequency or percent frequency, the shape is very similar. However, you want to be careful with your scale. So just for the sake of argument, if you pick any of these, so if you look at this one, this has number 18, and this is the height 18. So this one has the height 8. To the right of it, this has the height 13, and so on and so forth. So I hope it's clear. So coming up with the histogram, bars are adjacent. The horizontal axis uses the boundaries. Vertical axis uses frequencies in this case. Relative frequency histogram, again, as I said, it works in the same manner. Coming up with the histogram for the given, it's really not a big deal. As far as the horizontal axis is concerned, just the way it's given, you can choose to use 75 to 124 as the first one, and so on and so forth. But you can also make up your boundaries. Remember how we make up the boundaries. Look at this one. So the upper boundary for the first class is 124.5. So I'm going to write just the first class. So 75 to 124. That gives us here 124.5, which means the next class uses the same lower boundary, 124.5. The width is 50, so you can subtract 50 and you can add 50. So remember, the width is 125 minus 75, which is 50. So if you add 50 to 124.5, you get 174.5. You can subtract 50 from 124.5 and you get 74.5. And this is the histogram that you have. Very straightforward. And the largest one, of course, has the frequency of 24. So this number, this corresponds to 24, 11, 10, 3, and 2. Now, relative frequency is defined as frequency divided by total size. So the relative frequency for the first class would be 11 divided by 50. The next one would be 24 divided by 50, and so on. We remember that. I think this question was done already. And remember, the RF, the relative frequency, must add up to 1 or 100%. So this must add up to 100%, or we've made a mistake. The only time that it may not be 100% is due to round off error. If you have, for example, 99.9999%, or if you have 100.000, bunch of zeros and then 1%, that is acceptable. And so you graph it accordingly, and they look very similar. If you do the relative frequency or percent frequency properly, they end up giving us the same answer class. The shape is very close. Now, the thing you want to be extremely careful of when you set up your graph, this must read frequency, this must read percent. Make sure you have them accordingly. So the point being, histograms, whether we use the frequencies to make up the histogram or relative frequencies to make it up, the shape shouldn't be that much different. When we do histograms, here's what happens. We explore the data by analyzing the histogram to see what can be learned about CVDOT. C stands for the center of the data. V stands for the variation. D is for the distribution. O stands for the outliers. And T is time. And there are some common distribution shapes. Something that is bell-shaped, also known as normal distribution. A uniform distribution, the heights are the same or almost the same. Skewed to the right or positively skewed, or skewed to the left or negatively skewed. Again, those are just the shapes. I think most everybody is comfortable with this and remembers this stuff. Again, a normal distribution, it's almost bell-shaped, and we call it normal distribution. As far as skewness, a distribution that is skewed, if it's not normally symmetric, extend to one side. If it extends to one side, such as the right side is skewed to the right, or maybe skewed to the left. We are in essence repeating what we just mentioned. So if we have the histogram drawn properly, it sort of gives us the information that were mentioned here. Now what happens if the histogram is given? In this case, the histogram, when we look at the bottom, it says weights of the porters in grams, and the top, the vertical axis is the frequency in which it occurs. So use the histogram, and we want to find the following. We want to come up with the number of subjects. The reason it says estimate the number of subjects, because sometimes it may not be easy to read from the histogram. It may be that it's close, and that's accept. The width, boundaries, and there's a gap or what's happening with that is it normally distributed. Now, to estimate the number of subjects, it simply means add up the frequencies. So each bar has a height. You estimate the height, you add them up. So I hope everybody's clear the concept. Again, I'm going to put number 12 here for the first one. And if somebody reads it, I think everybody should read 12. But if you read, okay, maybe you think it's 11, it's not that big of a deal. I want you to know the concept is whatever that number is, look at the next one and the next one and the next one, add them up. That's how we estimate the number of subjects. What about the width? First and foremost, let's talk about the third one, the boundaries. These are the boundaries for the first class. And then these two would be the boundaries for the next class, and then you move on all the way to the end. I hope everybody is clear. So we have number 1, we have number 3 in essence. What are the boundaries for the first one is 5.5 and 5.6. And therefore, the width is the difference between the two. When you want to calculate the width, if the boundaries are given, so the width would be upper boundaries minus the lower boundaries of the same class. Whereas in the limits, it was upper limits minus lower limits plus 1 unit. Okay, don't mix them up. Okay, so we have those. And there is a gap here. As you can see here, the height is 0 in this case. So again, can be explained. And whether it's normal or not, clearly it's not a normal distribution. Number of subjects, you need to add those heights, 12 and 20 and 8, and all the way to, then there are 80 subjects, in this case, quarters. The width, as I mentioned, 5.6 minus 5.5. And the boundaries are given for the first one. There is a gap, and that means there are 2 different groups, and then it's again from 2 different errors. The first set is 40, the second set is also 40, but 2 different errors. You can look them up, and clearly it's not normally distributed. Now, I want to explain one more topic that I want to go through that fairly fast. We don't dwell on it too much. And that's assessing normality. This is a piece of information, pre-1964 versus post-1964. The way it was used, 90% silver plus 10% copper, and then afterwards was copper and nickel alloy. So that's why different weights in any event. If we want to look at normality, normal quantile plot, here's what we do. Could somebody read this one for us, please?
Normal distribution, the pattern of the points in the normal quantile plot is reasonably close to a straight line, and the points do not show some systematic pattern that is not a straight line pattern.
Okay, so the idea is that there seems to be a straight line if we set them up. Could somebody read this one for us?
Normal, if the normal quantile plot has either or both of these two conditions, the points do not lie reasonably close to a straight line pattern. The points show some systematic pattern that is not a straight line pattern.
Thank you so much. So this is not a normal distribution. Now, what I want to discuss is this last piece, okay, which really puts all of it together. Could somebody read this one in blue, please?
Normal quantile plot. A normal quantile plot or normal probability plot is a graph of points x, y, where each x value is from the original set of sample data, and each y value is a corresponding z-score that is expected from the standard normal distribution.
Thank you so much. So what is normal quantile plot? It has the pairs are as follows, x and y. Y is equal to the z, which is x minus mu over sigma. We will discuss that with more details as we look at the z-scores, and that is the normalization score, standard normal distribution, and it's coming up. But that's the idea, you plot those pairs. So in section 2.1, we dealt with frequency distribution for organizing and summarizing data. We looked at frequency distribution table and various parts of that, lower and upper limits, lower and upper boundaries, and class midpoint, percent frequency, class width. We looked at the procedure for constructing a frequency distribution table. And then we looked at the next section dealing with various graphs and, more importantly, histogram. Normal distribution and when it's skewed to the right or skewed to the left. Now, we're going to look at graphs that are really helpful and graphs that are not, graphs that enlighten and graphs that deceive. The key concept, common graphs that foster understanding of data, and some graphs that are deceptive because they create impressions about data that are somehow misleading or wrong, could be done on purpose or otherwise. Here's a dot plot and dot plots and its features. A graph of quantitative data in which each data is plotted as a point above some horizontal scale, and we stack them up. It displays the shape of the distribution, and it is usually possible to recreate the original list of data. It's important to understand what that means, the second part. That means you really have the data. Whereas when we look at the frequency distribution table, we don't have every piece of data. So here's a simple example. We want to construct a dot plot and find an outlier, if any. So the idea behind the dot plot is very simple, class. Okay, I want to make sure everybody understands what's happening. So at top here, you just come up with a line. You can call it number line even. You can come up with a number line even if you want. And now you look at the data and you come up with the scale that represents those numbers. And you can even, one easy way, whenever you want to do that, you can rank them from smallest to largest so you see what you have. And then you have this scale, you can, make up the scale that you want, something like, I don't know, 30, 35, 40, and you move on. So you set up, you make sure everything is covered. So for example, somewhere here, just to give you an idea, somewhere here is 80. So if you look at the very first number that is 80, I put a check mark at top of it. So I put a dot at top of 80. Now the next number is 94. I go find number, so this is, let's say, 85, 90, 95, and this one is 94. Then I put a dot for number 94. And I do that for every number. I stack them up. So if I have one more number that is 80, for example, just for the sake of argument, if I happen to have one more 80, then it goes at top of it, one more dot. I have one more 80, same thing, and again and again. I don't, but I said, if in case I do, you just keep on stacking them up. So if we do this carefully, it'll look something like this. So just as an example, I want you to see that number 56, we have two of them. That's why at top of number 56, there are two dots, and you can move on that way. So this is called a dot plot. Now, when we look at this, it appears there is a number that is way off, and that number is this one. It's way off, therefore it's an outlier. Now, it may be subjective here, but later on we give a precise definition as far as stats is concerned as to how we arrive at it. When we come across it, I go over that. There's a formula as to how we arrive at an outlier. We have outliers and we have extreme outliers, and each and every one of them has a formula. We go over that. But for now, just it appears that it's way off. And I think everybody's clear as to what we mean. That is a basic definition of an outlier, a number which is way out. Now, it's either too small or too large. But what does it mean objectively? That's what we're going to discuss mathematically.
Professor,
So,
sorry, I had a
yes.
question. So in regards to the dot plot, you just, in regards to like the horizontal, like the categorical like range distribution, do we just kind of, was there a specific process you followed to figure out like, okay, 35 to 40, 40 to 45?
No, absolutely not. You can even start, okay, just make sure you have your smallest number, okay?
Okay.
The smallest number is covered. The smallest number is 36, am I right?
Okay, yeah.
Just make sure it's, so the smallest number is 36. And what was the largest number? 90, is that 94?
Yeah, 94, yeah.
So we want to cover all of those. So make up
Okay.
your own scale.
Okay, just making sure, thank you.
Professor?
Yes.
Could there be more than one outlier?
Yes, of course.
Okay.
One of the things that happens, what statisticians do normally, they use trimmed data, okay, meaning they cut a percentage of the data from the top and the bottom, assuming we have enough data. Most of the time we may not. If we don't have that luxury, we don't. But if we do, they cut the bottom 5% and the top 5% to make sure there is no outlier, okay? But you have to have enough data to do that. And yes, you can have more than one.
Okay.
Absolutely.
Thank
But
you.
as I said, as far as the precise calculation of that, we'll see it later on how it's done.
Okay. Thank you.
Sure. All right. We're going to look at a different graph known as stem plot using the same example. Could somebody read that one for us?
Stem plots represents quantitative data by separating each value into two parts. The stem, such as the leftmost digit, and the leaf, such as the rightmost digit.
Perfect. Could somebody read that for us?
Features of a stem plot shows the shape of the distribution of the data, retains the original data values, and the sample data are sorted or arranged in order.
So what happens in this case, you really look at the data and you see there are two digits. Because there are two digits is fairly easy to pick. You look at the leftmost digit and the rightmost digit. You basically have a horizontal line and you go from the smallest to largest, and you see the smallest number was 36. So let's start with 3, 4, and you go all the way to 9. So as an example, for 80, we would write 8. And then to the right of it, we write the second digit, which is 0. Now let's stick with 80. The next one is 94. So that's 94. But I want to go back to 80. Anything that are in 80s will go next to this one. For example, The next one I see 82, if I'm dealing with 80s only. Then 8, 0, I'm going to write number 2. Now, we better go with the order, but let's stick with the 80s. Let's see what else we have. Let me just circle the 80s. We have 86, we have 88, we have 84, and I believe that's it. So now, even if you don't put it in order, it's okay, but it's a good practice to put it in order. So the next one would be 84. The next one would be 86. And the last one would be 88. And that would be for 8, 0, 8, 0. That means, so if I were to read this, from here, I should be able to get all my data back. I have numbers 80, 82, 84, 86, and 88. Now you do the same thing for all of them. So I hope it is clear as to what we have here. So stem plots and dot plots, they give us the whole data and the graph.
Question.
Yes, of course.
Would there be situations where the number would be like 82.5?
Yeah, I don't think for a case like that, they expect you to do the stem plot, but yeah, it could be, or the number could have 5 digits, and probably you cut it into 2 and 3 or 3 and 2, you know what I mean?
Yeah.
So the point being is the type of data that you are given, it makes it possible to do an easy stem plots. Okay, that's the concept.
Okay.
But yeah, I mean, for the sake of argument, if it's given as 88.7, you would put 8.7 on the right side. Okay.
So how do you separate them out in that case if there's like decimal points involved?
Again, you can't. I mean, if you are using the first digit as 8, and that is what you have to do, then if it's 88.7 on the right side, so the way you separate them, this would be 8.7. Okay, it's important that you have a gap. So 0, 2, 4, 6, 8, and the next one is 8. Let's say 7 because it was 88.7. But normally, again, it doesn't happen, class, because the purpose of the stem plot is to make sure you are dealing with the type of data that can be written in that format. And more importantly, they may actually give you this one, and then you come up with the original data, okay? So I wouldn't worry about that. The bottom line is to make, in essence, make life easier writing the numbers, okay, and making it easier to understand. So the concept is when you're dealing with the 30s, there's only one number. When you're dealing with 40s, there are no numbers. When you're dealing with the 50s, there are 3 numbers. When you're dealing with the 60s, there are 1, 2, 3, 4, 5, 6 numbers. That's the idea of the stem plot, being able to see and recognize that. Now, the next one is a time series graph, a graph of time series data, which are quantitative data that have been collected at different points in time, such as monthly or yearly. And normally, they reveal some sort of a trend over time. So with that being the case, here's an example. We are given women's median earning as a percentage of men's median earning from 1990 to 2010, and we want to see what's happening. Do we see a trend or not? So from 1990 to 2010, you got to plot the point, and then you can connect them with line segments. The idea is that you want to see what happens, what the trend is. Now, I'm going to assume everybody can do the graph. We are graphing and along the horizontal line. The first one, let's say here, is 1990. And then maybe you go to 1995 and you move on. Okay, some sort of a scale you use. Okay, or maybe use, if you have room, you use scales such that along the horizontal axis you have 1990, 1991 too. That would be the best, of course. Okay, if you could do that. And on the vertical side, then you have the scales from 0 to 100 because we are looking at a percentage, and you plot the points. I'm assuming everybody can do this. It's not a big deal. So along the horizontal axis, we have the years starting from some year and we move on. And along the y-axis, the vertical axis, we are given this percent, which represents women's median earning as a percentage of men's median earning. Is there any trend as we look at this graph? Does it appear to be a trend here? Anybody can notice any trend? What do you think?
Yeah, it increases.
Very good, it's going up. There seems to be that it's going up. And so the effect is that it could help close the gender gap when it comes to earning, according to this data. The bar graphs are similar to histograms. Graph of bars of equal width to show frequencies for categories of categorical or qualitative data. The bars may or may not be separated by small gaps. It shows the relative distribution of categorical data, so it's easier to compare different categories. It's very similar to histogram. Now, a Pareto chart is a bar graph, then it has an added condition. We put the bars, we arrange them in descending order, of course, according to the frequencies or percent frequencies. So therefore, the height goes down as we go from left to right. And again, it has the same feature. So here's an example. We want to construct the Pareto chart for this example. Can somebody read the question for us, please?
A study of retractions, admission of wrong claim in biomedicine showed 472 were due to error, 225 were due to plagiarism, 881 were due to fraud, 295 were due to duplication of publications, and 249 had other causes. Construct a Pareto chart. Among such retractions, does misconduct, fraud, duplication, plagiarism appear to be a major factor?
Thank you so much. Obviously, it's fairly easy to come up with the chart. I don't think anybody has any problem with the chart. I want you to pay attention to the numbers. 472, 225, 881, and 295, and finally 249. So we want to go from the largest, which is 881, were due to fraud. That would be the very first bar, and that's the largest. So along the horizontal axis, we put the categories. What are the categories? Would be fraud as the first one. Then which one is the second largest is 472. So this would be the first bar. This would be the second bar. Then we have 295, duplication. Okay, so everybody gets the picture. So that would be the horizontal axis. What is the vertical axis? Those numbers. And that's what we get. And I don't think one needs much to understand the situation. And clearly, when it says among such retractions, does misconduct appear to be a major factor? Obviously. The good old pie chart, everybody knows what that is. We've been dealing with that from, I think, elementary school. I hope everybody is comfortable with that. It's a very common graph that gives us categorical data as slices of a circle in which the size of each slice is proportional to the frequency count for the category. So how do we come up with this slice? Is 360 degrees times the percentage that you need to come up with, if you will. That gives you the angle, if you will, that you need for the wedge. And so with that being the case, we want to look at this case, and to come up with the pie chart, you need to know what is the total. Just as an example, if we look at 881, so the percent that we need for that one, okay, remember, you come up with a circle, and then you want to cut it into pieces. Okay, remember, this is 360 degrees when it covers the whole plane. So you have to divide 881 by, okay, now all of them, what is it, 472 plus 225 plus 881 plus 295 plus 249, and change this to a percentage. So 881 divided by the sum, that gives you the percentage. And you multiply it by 360 degrees, and that gives you the angle you need to represent the amount of fraud, if you will. So take a look at this. If you multiply this by 360 degrees, and I'm going to leave it for class to figure out this angle, okay? And wherever you put that and however you put that, it makes no difference. Now, you can do the same calculation for each and every one of them. The next graph we want to look at is called frequency polygon. Could somebody read this one for us, please?
A graph using line segments connected to points located directly above class midpoint values. A frequency polygon is very similar to a histogram, but a frequency polygon uses line segments instead of bars.
Thank you so much. A relative frequency polygon is the same thing in essence. A variation of the basic frequency polygon is the relative frequency polygon, which uses relative frequencies, proportions, or percentages for the vertical scale. This is an example of a graph. Let's look at an actual example to see how we go through the process. First, let's come up with the histogram. I don't think anybody has any problem with that. In order to come up with the histogram, remember, you know how to do that. And we have the boundaries. For example, the first one is 5.5 to 10.5. The frequency is 1, so the height is 1. And so on and so forth. We want to come up with that using relative frequency. If we wanted to come up with the histogram using the frequencies, we would use the second column. Now we are told to use the relative frequency. So that's what I mean. You want to be very careful when you read the question. So relative frequencies are defined as F over N. So this column you have to divide by the total. First you have to figure out the total. When you add up this column, you get N equals summation of F, and that's 20. So you divide this column F by 20, 1 over 20, 2 over 20, and the rest of it. And they obviously must add up to 1 or 100%. Now we have the horizontal axis, 5.5 to 10.5 to 15.5, all the way to 40.5. The heights are for the first bar 0.05, the second one is 0.1, and so on and so forth. So my assumption is everybody is very comfortable coming up with this histogram. So that takes care of the first one. The next one is the frequency polygon. So this question is asking for the histogram. It's taken care of. So how do we come up with the polygons? We need to look at the midpoints and connect them. So understand what are the midpoints. The midpoints really in essence starts from here. This is the midpoint for the first class. Now how do you come up with that? 5.5 plus 10.5 divided by 2, or 16 divided by 2 equals 8. So that's number 8. That is the midpoint for the first one. And right at top, it's here. The next one, you can calculate or just add 5. The width is 5. So add 5. You don't have to calculate all the midpoints. Just the first one is 8. And the next one, just add 5. Keep on adding 5. So corresponding to that is this one, and then this one, this one. So first let me look at those. So you connect those with line segments, everybody. Also, you really have to extend this to the left. So now you really go by the width of 5 here. I want you to know that. And you connect here. Same thing here with the width of 5. And you connect here. Okay, you add, if you will, 5. So that's the polygon. So it looks something like this when you're done.
Professor, I just have one question.
Yes.
To the beginning and the end of the graph,
yes.
You have to add half of the width. Is that what it is?
Let me just go back and show you what I mean by that. First, connecting those parts, the midpoints was clear. Now remember what's happening. If this number is 8, right?
Yeah.
You can go 5 units to the left. That's one way to do that, and gives you 3. or from 5.5, go half of the width, 2.5 to the left. Either one leaves you number 3. Is everybody clear?
Yeah, thank you.
Sure. So look at this one. Remember what's happening. From 8, you go to the left, and from 38, you go to the right. Now, from there, the midpoints, the first midpoint minus the whole width. The last midpoint plus the whole width. So this one you add a width. This one you subtract a width. Okay, as far as knowing precisely where you end up. Does that make sense to everybody?
Yes.
All right.
Yeah.
For
Let's
the
go.
frequency polygons, do you always use the midpoint?
Yes, yes.
Okay.
This is how we graph polygons. All right, let's go to ogive. Now, in order to come up with the ogive, the very first thing you have to use is a cumulative frequency distribution table. So you got to come up with that. So first, this is the given. There's nothing brand new. But how do you come up with the cumulative frequency distribution table? If you recall, I said just either use the boundaries or limits, whatever is given. In this case, the boundaries are given. Okay, so you keep the lower limit, in this case, the lower boundary of the first class, and it becomes the lower boundaries for each and every one of the classes. And the upper boundaries remain intact, and then you add up the frequencies. The first class, the frequency is 1 and it doesn't change, but the rest of them you add up. So first you write them in this fashion. The lower boundaries all change to the lower boundary of the first class. So this 5.5 will take over as the lower boundaries for each and every one of those. The upper boundaries remain intact. Now, what about the second column? Again, the first one doesn't change, becomes 1, but the next one is 1 plus 2, and then you keep on adding. So those are the frequencies. But remember what we had. We were supposed to do this for the relative frequency, and therefore, we are going to divide this again by n. And the last one, it's extremely important to remember, the last one is always 1 or 100%. The last one is always 1 or 100%. And so we have this. Again, this shouldn't really take that long for you to figure out. We have gone over that. I just wanted to go through the procedure to remind you. So we have that. So we have the class boundaries for the cumulative frequency distribution table. We have the frequencies, and we are interested in relative frequencies. Now, how do we come up with the ogive? The way the ogive works, again, you put the boundaries on a horizontal line, and you put the frequencies or relative frequencies. In this question, we are putting the relative frequencies on the vertical line. So construct an ogive. It's a line graph that depicts cumulative frequencies. So ogive goes with cumulative frequencies. And ogives use upper class boundaries and cumulative frequencies or cumulative relative frequencies of the classes. What do we mean by that? The lower boundary of the first class, okay, so you have your horizontal line, you have your vertical line. Your horizontal line are the boundaries, end of the story. What about the vertical? The vertical lines is either the frequencies or relative frequencies. And which one are we using for this question? The question was asking for relative frequency. That's why we're going to use that. But you have to read the question and make a decision accordingly. So with that being the case, we are going to use the relative frequency. So we go from the smallest to largest, or relative frequency or percent frequency, it doesn't matter. So 0.05 or 1 out of 20, okay? And you keep on going all the way to the end, and it has to be 1. So how does this work? How do we connect the line segments? I want everybody to pay attention to the lower limit of the very first class corresponds to 0. The upper limit of the very last class corresponds to 1 or 100%. Everything else goes in between, putting together as line segments. What lower limit of the first class is 5.5, and it corresponds to either 0 or 0%, depending upon whether you're using the frequency or percent frequency. Upper boundary of the last class is 40.5, and this number corresponds to either 1, or if it's a percent frequency, 100%, or if it's frequency, this must correspond to the value of n. In other words, if we were doing the frequencies, that would be number 20. So those are the first thing I want everybody to understand. So the lower limit of the first boundary corresponds to 0%. The upper boundary of the last one corresponds to 100%, or n. What happens afterwards? You look at the upper boundary of the first class. So the upper boundary of the first class is 10.5, and that corresponds to either 1 or 1/20. So look at this number. At top of 10.5, you either have number 1 or number 0.05. You use 1 if you're dealing with frequencies. You use 0.05, and we are going to use 0.05 here if you're dealing with percent frequency or relative frequency, okay? Now, for 15.5, you put 3 or 0.15. For 20.5, you put either 6 or 0.3. For the next one, you
Professor,
put either 11. Yes, go ahead.
I have a question. Is it going to tell us when it's cumulative relative frequency on the y-axis, and then we know whether to put 3 or 0.15 or 6?
Yes, the question, if you go back to the question that we did, previous page, it said specifically relative frequencies, and I underlined it.
Okay, thank you.
Sure. Now, what is it good for? It can help us answer a question such as this one. What percent of runners ran 22 miles or less? In which case, along the horizontal axis, you locate number 22, and along the y-axis, you do your best to find the answer, and it's about 41%. All right, now graphs that deceive. One of the problems is a non-zero vertical axis. A common deceptive graph involves using a vertical scale that starts at some value greater than 0 to exhibit differences between groups. Okay, for example, in this case, we notice it starts at 10% OxyContin and placebo.
Sorry, Professor, I think I have a question on that last slide.
Go ahead. What's your question?
I was curious, could you change the width to make it fit the 22 miles?
I'm sorry, what about 22 miles? 22 is a number between 20.5 and 25.5.
The boundary, could you change the width to make it less than 22?
Okay, you want to make the width smaller than 22, is that what you're saying?
Yes. Could you do that, or that was the part I was confused on?
I'm not too sure if I follow the question. The width is 5. If you look at the class boundaries, the width is 5, and that remains constant for each and every one of the classes. When you refer to the width, you're referring to the width of the class, am I right?
Yes.
Okay, the width of the class is 5, and you can't change it.
Okay, I was just curious. Thank you.
Sure. All right, so if you have a non-zero vertical axis, that is one that is really not a good idea. Take a look at what happens when we use the proper axis. Take a look at the change, 10%, which is wrong versus 0%. When you look at the 10%, it appears that the placebo has basically no effect. So it is extremely important to be careful with. So always examine a graph carefully to see whether a vertical axis begins at some point other than 0. Also, when we look at pictographs, first of all, drawing of objects called pictographs are often misleading. Data that are one-dimensional in nature, such as budget amounts, are often depicted with two-dimensional objects or three-dimensional objects, and that is not correct. So by using pictographs, artists can create false impressions that grossly distort differences by using the simple principles of basic geometry. When you double each side of a square, its area doesn't merely double, it increases by a factor of 4. In other words, 2 squared equals 4. When you double up, you multiply the area by 4. When you double the side of a cube, then it's 2 cubed. It's 8 times larger. 2 cubed. That's how we arrive at the 8. So when you look at this case, this is misleading. A one-dimensional data with a three-dimensional data. This is a fair and objective pictograph, which is a data that is using very simple bar graph and clearly give us the exact situation starting, pay attention that starts with 0. Whereas if you look at the left side, it appears there's a huge difference between the two. When you multiply it by 4, it gives you this proper graph. When you do it here, 4 cubed, because it's three-dimensional, it appears that it's 64 times larger, which is not proper. All right, we're going to go to the next section. All right, I want to look at scatter plots, correlation, and regression briefly because we covered this in a later chapter. We looked at frequency distribution tables, histograms, and we looked at graphs that are good and useful, such as dot plots, stem plots, time series graphs, bar graphs, Pareto chart, pie chart, polygons, ogive. And then we looked at some pictographs that can deceive the reader. So we want to be careful of that. All right, key concept. Could somebody read this one for us, please?
Yes. Analysis of paired sample data, correlation, and the role of a graph called a scatterplot. Introduction to the use of the linear correlation coefficient, linear regression, which involves the equation and graph of the straight line that best fits the sample paired data.
Thank you so much. So we are looking at scatter plots, correlation, and regression. Could somebody read the correlation for us?
Correlation association exists between two variables when the values of one variable are somehow associated with the values of the other variable.
Could somebody read this one, please?
A linear correlation exists between two variables when there's a correlation, and the plotted points of paired data result in a pattern that can be approximated by a straight line.
And this last one, could somebody read that, please?
Scatterplot. A scatter plot or scatter diagram is a plot of paired XY quantitative data with a horizontal x-axis and a vertical y-axis. The horizontal axis is used for the first variable x, and the vertical axis is used for the second variable y.
Thank you so much. Again, in later chapters, we discuss this further, but a couple of things. First of all, correlation refers to a relationship and association, no more. It's not about causation. It doesn't show any cause and effect. Now, correlation doesn't have to be linear, but we are mostly interested in linear. There may be other correlation. For example, a quadratic relationship between x and y. And then scatter plot is very simple. You plot the pairs. By the way, when you plot the pairs, as far as the correlation is concerned, x comma y versus y comma x, the correlation doesn't change. All right, so when we look at this example, look at the first one and look at the second one. The first one is dealing with the circumferences of the waist versus the arms. And the second one, weight and pulse rates. Now, clearly, there seems to be something going on here, some sort of a linear correlation in the first case, part A. But if you look at part B, is all over the map. I can't see a linear correlation. So therefore, we say, yes, there is a correlation, and we say pattern of the plotted points suggests that there is a linear correlation. So in short, the answer is yes, there seems to be a linear correlation between what? The waist circumferences and arm circumferences. Whereas between waist circumferences and the pulse rates, we don't see anything. The pattern doesn't indicate any correlation. The next thing I want to discuss is the correlation. Linear correlation is between -1 and 1. And this is just like the slope. I'm going to remind you, everybody remembers the y equals mx plus b. And
Yes.
when m is positive, the line looks something like this. And when the slope is negative, it looks something like, and that y equals mx plus b is called slope intercept format of a line, a linear equation in slope intercept format. So R is the linear correlation coefficient. It's between -1 and 1. And if it's close to 1, that there is a correlation, positively correlated. If it's close to -1, negatively correlated. If it's in between, like 0 or close, then there is no relationship. Of course, the first and the second one are very clear. By the way, in part C, there seems to be a quadratic relation. I want you to know that, okay? A non-linear relationship. There's a quadratic relationship. This looks like a parabola. Everybody remembers that. Y equals ax squared plus bx plus c. Okay, just, yeah, you don't have to worry about it, but just to refresh your memory. And the last one, there seems to be nothing there. All right, analyzing the scatter plot. Could somebody read that one for us, please?
Positive linear relationship exists when the points fall approximately in an ascending straight line and both the x and y values increase at the same time.
Thank you. Which simply put means when x goes up, y goes up. Could somebody read this one for us, please?
A negative linear relationship exists when the points fall approximately in a descending straight line from left to right.
Thanks. That means when x goes up, y goes down. And a nonlinear relationship exists when the points fall in a curved line. An example of that is part C. And there could be a case when no relationship exists. Sometimes it happens, in which case when there is no specific pattern which can be described, as it is the case for the last one. All right, we want to see if there is a relationship between the number of wet bike accidents and the number of wet bike fatalities based on the following data. And so plotting the pairs shouldn't be a big deal. We can plot those pairs. This is X and Y. This is another X and Y. This is another X and Y. And when we plot those, there seems to be a positive linear correlation according to the scatter plot. The pairs and seeing the scatter plot and a relationship. Again, this will be discussed with more details in later chapters. So now we are going to look at the following pairs. As you see, the pairs are given, and that simple scatter plot is given. And the scatter plot doesn't seem to show if there is a linear correlation. Definitely, it's not clear. Now, what I want to discuss, which is coming up, and we will look at it with more details, is the following. Here's the p-value, and here's the idea behind the p-value. Again, this becomes very clear when we discuss it in later chapters. P-value, if there really is no linear correlation between two variables, the p-value is the probability of getting paired sample data with a linear correlation coefficient R that is at least as extreme as the one obtained from the paired sample data. Now, if you look at the information on the right side that has been given to us by technology, in this case, StatDis, if you run the data, it gives you, one of the values that it gives you is the p-value. And normally, what it really means, you compare it to the specific choice of alpha. Again, what is alpha? Probability of making type 1 error. We're going to discuss that in later chapters. It's put here. I want you to at least have an idea how that works. If the p-value is large, then you, in the test of hypothesis, we have a null and alternative hypothesis. And in the case of a null hypothesis, there is no correlation, H0. Again, we are way ahead of ourselves, but it's coming up in this section. I wanted to mention that. And when p-value is, calculated, you compare it to the choice of alpha. So this is compared to the choice of alpha. If it's larger than that, you don't reject H0, which means there is no correlation. And if it's smaller than that, you reject the null hypothesis. That means there is a correlation. You don't have to worry about that as far as the exam is concerned, but I want you to see that here's the explanation. The p-value of 0.294 is high. It shows that there is a high chance of getting a linear correlation. In this case, the linear correlation is this number from the technology, 0.591. By chance, when there is no linear correlation between the two. Because the likelihood of getting R equals 0.591 or more extreme values is so high, 29.4% chance, we conclude there is not sufficient evidence to conclude there is a linear correlation between shoe print lengths and heights. Only a small p-value such as 0.05 or less suggests that the sample results are not likely to occur by chance when there is no linear correlation. So a small p-value supports a conclusion that there is a linear correlation between the two variables. What do we mean by that? Let me just see if I can explain this in a manner that it at least makes some sort of a sense here. You compare the p-value to alpha. If it's larger than alpha, by the way, in many cases we choose alpha to be 0.05. Then what you do in the test of hypothesis coming up, you do not reject the null hypothesis. And in this case, rho becomes 0 in essence, and there is no correlation. If the p-value is less than alpha, and remember, alpha, by the way, doesn't have to be 0.05. Most of the time, we choose it to be 0.05. And if it's less than that, then you reject H0, which says there is no correlation. So again, in the test of hypothesis, we write H0, rho is 0, and H1, rho is not 0. We are way ahead of ourselves. This is coming up in later chapters. I don't want anybody to worry about that. All right, so correlation and regression will be discussed in later chapters. So if we look at this exam, all I want you to see is really the following. What's happening here, the p-value is very small. That's what I want you to see. And therefore, there's a correlation. The scatter plot shows a distinct pattern. The value of the linear correlation happened to be 0.81. This is where it comes from. This is 0.81. Okay, from the technology, we have the value of R, we have the value of P. Now, the scatter plot shows there is a linear correlation, and by the way, the linear correlation is 0.81. Needless to say, the larger the number, the closer to 1, the better the linear correlation, the stronger the linear correlation, and the same thing closer to -1, okay? And so p-value happened to be very small, so we have sufficient evidence to support the claim that there is a linear correlation. That's how we do the writing when we do the test of hypothesis. I just want you to see the concept here. And what is a regression? Given a collection of paired sample data, the regression line or line of best fit or least square line is the straight line that best fits the scatter plot of the data. In other words, is there a way to calculate that line, assuming the line in red, when you go back to the plot, is the line of interest? Yes, the process is called the regression, and in fact, it is given again with the technology. Now, there is a process, we go over that, and you'll see it can be done by hand. Needless to say, it takes forever, but it can be done by hand. So if you look at that one, again, we are just reading from the technology. The general form of the regression equation has a y-intercept of b sub 0, which is 80.93. I didn't write the rest of them, 041. And the slope, or b sub 1, is 3.2185. It continues indefinitely. I did round it to 2 decimal places. And so the equation that is used is as follows. We use y hat, really not y. This is the formula. Y hat as b sub 0 plus b1x, where b sub 0 and b sub 1 are given. You put it in 80.93 plus 3.22x. What does that mean? That means that if we will do the interpretation of this line, the height is 80.93, let's say, or even 80.9, 80.93 or 80.9, and then 3.22x. What was x? The shoe print length. So the length of the shoe print times 3.22 must be added to 80.93, and roughly that gives us the height of the person.